So this is the subject I'd like to talk about today. Mechanical behavior of steel bridge deformed by collision. It happens sometimes that a truck running on the highway collides with the overpass, causing some damage on it. This is one of those bridges. A truck must have collided with around here, and then some damage around here. And I was involved in the investigation of the safety of this bridge several years ago. This is a view from underneath. The bridge has two main girders and orthotopic steel deck. It has longitudinal stiffeners and then cross girders. And it carries two water pipes as well. So there are some struts to support them. These slides give you some idea about the bridge. This is a cross section, and you can see that the distance between the two main girders is 3.5 meters. So the bridge is not so big actually. It carries a traffic only in one direction. And the truck collided with G2. And this is more details about G2 and its vicinity. This is the schematic of the damage. The G2 girder deformed outward. This was because expressway slopes. Traffic goes in this direction, and the clearance below G1 is larger than G2, than that of G2. So the truck runs safely below G1 but collided with the G2, causing this damage. So after the owner found out the problem, the residual horizontal displacement of the lower flange was measured, and this is the result, and the maximum displacement found around section 9, which is 186 millimeters. We also observed around here the bottom surface of the lower flange somehow scratched, and there was the removal of coating around here. So we have concluded that the collision occurred around here. The deformation is not the only damage caused by the collision. There are some other damages shown in these photos. This shows the bent transverse stiffeners like this, and the struts were separated from stiffeners like this. There were bolts, but they had gone. And this is the buckled transverse stiffeners here. And then we observed some transverse stiffeners were separated from the web because the welding was fractured. But fortunately, there were no damage around bearings and no cracks in the main girder. So the major concern was the deformation of the girder. At section 11, we observed this phenomena. A strut was separated from the transverse stiffener, and then it was supported by the two main girders like this. Lower flange and the strut were in contact. The measurement close to 11, section 11, was 148. And then with some other values, we evaluated that the horizontal displacement across section 11 is 143 millimeters. Therefore, for this phenomena to take place, the horizontal displacement at section 11 by collision, the maximum value has to be greater than 143, and the residual displacement had to be 143. If not for these struts. So this much we can tell from this phenomenon. Then we conducted analysis of the bridge by the finite element method using abacus. This is the finite element mesh. Shell elements were used except the struts, which were modeled by beam elements, And then we apply the load in the horizontal direction at around section 9. And then we obtain this displacement at section 11. This is the result. Load, displacement, horizontal displacement at section 11. We got this relationship. And then from this figure, we can tell that the collision load must be greater than 1015 but smaller than 13 Newton per millimeter for that phenomena at cross section 7 to take place. We observe the deflection of the strut at section 11, 8 millimeters, and we know that we believe that this one caused by the actual load coming from the lower flange. They are in contact. And then we know the lengths and the cross-section dimensions, so we conducted nonlinear analysis of the struts, and the numerical analysis tells us that 41 kilonewton, actual load of 41 kilonewton acting between them. So in the next analysis, we including this effect, actual load, and the result is this red one, B. And this result shows us the collision load must be 1584 Newton millimeters, so that the residual displacement is 433 millimeters with the actual load of 41 kilonewton at the end. And this is the result of residual horizontal displacement. And this solid line is the computed result, and these red circles, solid circles, are measured values. They are in good agreement with each other, which we believe just by our numerical approach. Then we try to figure out the influence of the collision damage, and to that end we took the damaged girder from the damaged bridge, the previous numerical results, and we applied 2-point loads at section 8 and section 10 because the severe damage occurred between these two sections. Point C is the point of focus in this analysis. This is the numerical result, load P versus vertical displacement at point P. Red one is the result for the girder without any damage, right? And if you give the collision damage, the load displacement curve becomes this blue, damage 1. That is the girder with the collision damage. And you can see it, initial stiffness becomes smaller, 40% smaller actually from the original girder. But the bending strength reduction is very small, almost 0.8% only. So the collision damage does not reduce the safety of the girder, it appears. Further study the influence of the collision damage. We increased the damage by a factor of 1.5. Then the result is this damage too. As you can see, initial stiffness further reduced, and now 31% smaller than that of the original girder. And the influence on bending is also there, but the value is still small, 1.5% only. So from this result, we may conclude that the collision damage does not threaten the safety, doesn't seem to threaten the safety of the bridge, considering that the factor of safety in Japanese design standard is 1.7. There are two factors that the collision induced. One is the geometrical change, configuration change, including the horizontal displacement that we have discussed a while ago, and another one is the residual stress induced by the collision. So to see the influence of these two factors, In the next analysis, we conducted without residual stress. That is, here in this case, damage 1 prime. Damage 1 is the girder with the collision damage, and damage 1 prime is the girder with only a geometrical change, and the result is brown one, low displacement curve. The difference between damage 1 and damage 1 prime is not so much. Initial stiffness reduction is reduced from 14% to 12%, slightly recovered. Bending strength also changed, but it's almost none. So the influence of the residual stress turned out to be very small. Geometrical change has a larger influence on the mechanical behavior of the girder. We did the same for the girder with the larger damage. This is original low displacement curve original girder, and this green is the result of the girder with a larger damage, and we remove the residual stress from damage 2. That is the damage 2 prime, and then low displacement curve for that is this yellow line. Initial stiffness a bit recovered from 31% reduction to 25% reduction, and bending strength also influenced slightly by the initial residual stress, but the difference is again small. So from this result also we can say that the influence of geometrical change is larger. Concluding remarks: the residual horizontal displacement was reproduced very well by the finite element analysis. The influence of the damage due to the collision was investigated. The initial stiffness was found reduced by 14%, and the reduction in the bending strength was 0.8% only. Even when the damage was increased by 1.5 times, the reductions in the initial stiffness and the bending strength were still limited. The influence was found attributable mostly to the configuration change of the girder. It may be concluded that the deformation of the girder due to collision doesn't necessarily threaten the safety of the bridge. It needs to be noted, however, that the damage other than deformation, if any, could lead to considerable reduction in safety. So we still need to be very careful when we find the collision damage in the bridge. So this is all I want to say today. Thank you very much for your attention.